Today we're doing the unsigned square root algorithm for a term project. We didn't want to mess with imaginary numbers, so we chose the unsigned route for using the section under integer arithmetic. Document information that we found for this algorithm was written by 4 authors from India. Published date was October 2013, and it was intended to use on the FPGA board. They designed it, implemented it, and that's what the paper is based off of. Basic information about this algorithm: it's an 8-bit number algorithm that can be expanded for other sizes for numbers. Numbers treated as unsigned because we didn't want to mess with the square root of a -1, which is equals I. So the range that you can input is 255 to 0, which is all ones and all zeros. You must include all 8 bits, including leading zeros. It's similar to the division algorithm that does the restoring that we learned in class. And we also used a data type called bit set in C++ that basically does the decimal to binary and binary to decimal conversion, so we can do our math a lot simpler instead of using our own subtraction and addition methods. First, you want to start with your 8-bit unsigned number. You want to split that up. Each one of those bits you want to split up into groups of 2, so you'll have a group of 4 for your number that you inputted, and then you want to append on 4 groups of 2 of zeros, just like the picture shown there. The decimal is just there to show, hey, the left half is your number and the right half will be the fraction. So the initial step, you take the most 2 significant bits that your number is inputted. In our case, it's 0, 1. This is obviously the square root of 93. So you subtract 0, 1 on your first step, no matter what. If the answer that you get from your subtraction is positive, you append 1 to the rooted answer. Currently, the rooted answer has nothing into it, so if it's negative, you append 0 to the rooted answer and then restore by re-adding. So as you can see on the picture on the right, on our first step, you got a positive value, so we appended a 1. Then our next step, you subtracted, and then it got to a negative value, so you're restored. You can see that it's not completely shown here on what to do, and we'll show you in our program on how everything's implemented. Basically, the next 7 steps you'll do is you drop down the next 2 bits and append to either the restored value or the difference depending on what your previous steps were. So if it's positive, you will have a difference, basically, or if it's negative, you'll have the restored value, and we're going to call that x in this case. You take the 2 bits so far in the answer, so since on the first step in our example we had a 1 since it was positive, you drop that down and append 0, 1. As you can see here, where the arrow that says append 0, 1, it's 1 since it was positive. The previous step was positive. You append 0, 1. So then you do the binary math of x minus y. If the result is positive, you append 1 to the answer. If it's negative, obviously you restore and append 0 to the answer. Here's the example that we used. It's not lined up perfectly. It's as good as we could get it. The final answer down at the bottom, 1100, 100, 111, is irrelevant. We do not use it in any of the calculations, so it's basically just a byproduct of getting the answer. Positive attributes of this algorithm, it's similar to the algorithm learned in a class that was for the division. It basically does the restoring if it was negative. If it was positive, it kept on going. It's pretty easy to understand. Negative attributes of this algorithm, it's not very accurate. As you can see, if we did the square root of 93 like we did in our past slides, you get a number of 9.625 if you converted it to decimal. Using a calculator, if you did the square root of 93, you would get 9.643, and it's off by 0.0186, which, depending on what your target platform is, if it's building rockets, this algorithm probably isn't very good for it. If it's other things, it's pretty fair. Depending on, it's just a pick or choose of which algorithm you want to use. Our reference, you can find our paper later. I'll get into our demo for our program right now, showing you each step on how everything is working in our algorithm in a more visual way. We come in here with our program. As you can see, this number will be treated as unsigned. All numbers inputted are unsigned, and it must be exactly 8 bits. You can't go any more, you can't go any less. Must have the leading zeros. So if we do the example like we did in the PowerPoint slides, 0, 1, 0, 1, 1, 1, 0, 1. Step 1 in it is 0, 1 minus 0, 1. You get all zeros. The answer is positive. So you append 1 to the answer, and the current answer so far is 1. So that's the first step. You always subtract 0, 1. So step 2, you get your You get your answer, all zeros, and then you append 01 to that top number, minus your current answer so far, so which is that first one, and then you append 01, and then if you do the subtraction there, you get 6 ones and 2 zeros, and that answer is negative. So you append 0 to the answer and restore the value. So your answer so far is 1, 0. For the next step, step 3, it's take the restored value, append what our we get a restored value and append our drop down next 2 bits of the previous answer, minus our previous answer or our regular answer, which is 1, 0, and then we append 0, 1, and you get 7 ones and a 0, which is negative. So you restore the value, append 0 to the answer, so our answer so far is 1, 0, 0. For our next step, step 4, you do the exact same thing. You take the answer and append 0, 1, and drop down your next 2 bits on the left half. As you can see right here, you append 0, 1, and this is our answer right here, then append 0, 1. Subtract that, you get an answer, which is positive. Append 1 to the answer, as far as 1, 0, 0, 1, which is, since it's 4, that's halfway through our algorithm, that's our actual number, not the fraction yet. So the next 4 steps is going to be the way we calculate our fraction. It's none different, other than instead of dropping down your 2 bits that you got from your number you inputted, it's just going to be zeros from here on out. So you append zeros on the left half. So right here you append these 2 zeros, you minus the answer so far, and you append 0, 1 to it. It equals a positive value, so you get append 1 to the answer. So your answer so far is 1, 0, 0, 1, 1. You do the same thing for step 6, and you get your answer so far as 1, 0, 0, 1, 1, 0. Step 7, you do this exact same thing. The answer so far is 1, 0, 0, 1, 1, 0. And then you keep going. Step 8, it should be your final step, set for an 8-bit number. You get 1, 0, 0, 1, 1, 0, 1, 0. So if you wanted to see our answer, since we go halfway through, that's our number, our whole number. You put a decimal after your 4th number, or your 4th bit, and then the rest of it, you get your fraction. So 1001.1010 is the floating point number. If you translated that into decimal, you would get 93.625. As are shown on our slides, that is the correct answer.